So for the second half, now first let's complete this topic, linear search topic. Yeah. Now we are in the situation. Yeah. We want to describe the overall performance, overall efficiency of this algorithm. Yeah. The question, what is the best way to describe the overall efficiency? Yeah. Definitely, we cannot use the best case, right? Yeah. Too optimistic. Yeah. We cannot use worst case. Yeah. So we need some number between these two cases. Yeah. But what is the best way to represent the overall efficiency of this algorithm? Yeah. All right. So answer that question, we need to consider all the possible cases. And we need to combine all the possible cases. We cannot miss anyone. But when we combine them, we need to find a fair way. How to combine them? There are so many different ways to combine all these cases. But which way is the best? Yeah. So that's the question we need to answer here. All right? Yeah. The measure should include all the cases. Yeah. First. Second, yeah. Here we list all the cases. Yeah. But many times, yeah. So here, how to know all the cases? Because later in our, we will solve many other computing problems. Sometimes you may not be able to list all the cases because there are too many cases. For example, sorting. When you need to sort an n-element array, when that n number is a relatively large number, how do you list all the cases? Too hard. Although it's possible, now we can use computer to help us list all the cases. But people don't want to go that direction. Yeah. All right. Yeah. How to combine all the cases to best describe the overall efficiency? That's the main question we need to answer here. Yeah. All right. Yeah. Need to make appropriate assumptions. Now, for these questions, the given information is not sufficient. Yeah. Because based on the given information, we were not able to answer the question. Yeah. So we need to make some appropriate assumptions to answer this question. Yeah. Yeah. The assumption should be fair, should reflect the real world situation. Yeah. All right. C.2, average case efficiency. So in this topic, we need to discuss this concept, average case efficiency concept, and how to calculate average case efficiency. All right. Analysis. Yeah. That's our data. Yeah. All the cases. Yeah. Question, how to combine them? The best way to combine all these cases. All right. Let's make some assumptions. Yeah. The first assumption, yeah, assume that all these, the first n cases, because these cases, you can find the element that matches the given key k. Yeah. Yeah. So for the first n cases, we assume they have the same probability. Yeah? Same probability. Okay? That's reasonable, right? Yeah, that's reasonable. Yeah. All right. But that assumption, still not enough. We need another assumption. Yeah. Because for the no match case, what's the probability for this last case? Well, we do not have the data, right? We do not have the data. So here, we also need to know the probability for the last case. All right, so here, our assumption. Probability for the index case. Yeah, the first n cases because it returns a valid index. Valid index, okay? Yeah, our function returns a valid index. Yeah. So we can assume that probability is given. We use p constant. Yeah. This p is a constant. It should be given or known. Yeah. Yeah. P. Yeah. Then the no match case, yeah, the function returns -1. Yeah. That's the last case. Yeah. The complementary part, that is 1 minus, yeah, the p is between the range, we know, between 0 and 1 inclusive. Yeah. So the -1 case, the complementary part of that p, 1 minus p. Yeah. All right. But in the real world application, that p, so how do we know this little p? Yeah. People can do experiments. People can do statistics. Yeah. People can use history data. Yeah. Because when you apply the linear search algorithm on your business data, you should have history data, right? Yeah. So people use the statistics from the history data to estimate this p. Yeah. All right. Yeah. All right. Yeah. So here we do not need to worry about it. Okay. So there is some reasonable way to get that p, little p. Yeah. All right. Yeah. Yeah. Dynamic statistics. Yeah. Because when you use this algorithm, so you process your current data. Yeah. The data you have processed, you can use to do the statistics, right? Yeah. All right. Yeah. Now, we can use the given information here at this point to calculate the average case efficiency. Yeah. All right. Yeah. So how to calculate? Yeah. All right. Yeah. Let me put all these in. Small index cases, group them as our first subcase. The index case, that's our first subcase. Okay. Second subcase, the missing case. Yeah. No match. Yeah. Yeah. All right. So the second case. So 2 subcases. Yeah. All right. In these 2 subcases, let's look at it. What is the average case efficiency for each subcase? Okay? Yeah. The first subcase, when we look at the average case efficiency for the first subcase, we can ignore this no match case. Yeah. Ignore. Right? What's the average case for all these n cases? Yeah. The average number for, because we use this assumption that all these n cases have the same probability. Okay? Same probability. Yeah. All right? So they share here each case same probability and one nth probability. Yeah. Each case has this 1/nth probability. So adding together total n. Okay? Total n under the condition k falls into all these n cases. All right? Now, under that condition, each one has 1/nth probability. All right? Now, we can calculate the average case efficiency for the first subcase. That is, take the average, right? Our usual definition of the average, 1 plus 2. Yeah, so you add up all these n numbers divided by n. Okay? Yeah, divided by n. Yeah, all right. By our summation formula, that is 1/2 times n plus 1. Yeah. So that is the average case for first subcase. All right. Second, what is the average case efficiency for second subcase? Second subcase, you only have one case, one number. So what is the average number for this one number? Only this number. Average for this number is this number. Yeah. So the average case is a second subcase, n. All right. Now, our last step, you need to combine these two numbers. Yeah. The final step, combine these two numbers. What is the best way to combine? You need to use the probability numbers for these two subcases. The probability for the first subcase, little p. The probability for the second subcase, 1 minus p. Yeah. When you combine them, here we used a concept called the weighted average concept. Weighted average. Yeah. All right? Weighted average concept. All right. So how do we define the weighted average to combine these two average case numbers? Yeah. The weight for the first average, we use the probability as its weight. This little p, that's the weight. Okay? That's the weight for the first subcase. The weight for the second subcase, 1 minus p. Weight, second subcase. All right? So this combination we call the weighted average. Okay? The contribution of each average case numbers, what's their contribution share? The probability, we use the probability number as the contribution share. Okay? The larger the p, more contribution, right? Yeah. Yeah. Similarly, yeah, the second weight, the contribution part for the second subcase. Yeah. So this is the most reasonable definition of weighted average. Yeah. All right. And look at the dominant term, yeah, because this whole expression. Yeah. So this whole expression, that's our overall efficiency. Yeah. But when we use this overall efficiency expression, yeah, this expression looks a little long. Yeah, a little long. Yeah. Sometimes, yeah, so here in our analysis of computer algorithms, it's very common. We want to make our final expression as simple as possible. Yeah. To do that, sometimes we want to ignore the minor terms, because the impact of those minor terms, very little, we can afford to ignore those minor terms. Yeah. Here, for example, yeah, n plus 1, this plus 1, very little, right? Yeah. So we can ignore this plus 1 to make it a little simpler. Yeah, to make an expression a little simpler. Yeah. Yeah. So that's very common. Okay? Yeah. All right. So we use the approximation result. But that approximation result much simpler than the exact expression. All right. So here we define this dominant term concept. No. We only keep the dominant term. We use the dominant term of our efficiency function to represent the whole efficiency function. Why we do that? Because we want a simpler expression. That's the reason. All right. So here, the dominant term of this function is this one. How do you see it? dominant term. Okay, all right. After you ignore this +1, you add up the numbers. Yeah. So this is your dominant term. Okay. Yeah. The variable is n. The coefficient of this n variable 1 minus 1 times n. That times p. Yeah. Yeah. So this concept, we will use it in our module 2. Module 2, when we study the efficiency estimates, we need to use this concept, dominant term. Okay, all right? Yeah. So now you can see we complete discussion of this average case efficiency. How to calculate? Weighted average, that's the right way to calculate average case efficiency. Yeah. All right. Yeah. The dominant term gives a good approximation. Yeah. And the minor terms can be ignored without significant loss. Yeah. But at the beginning, some people may not feel comfortable ignoring the minor terms. Yeah. So why ignore so many terms? Yeah. Later you will see the part we ignore, the percentage of that part extremely small. So we should not worry about it. The percentage, very little. Yeah. So the dominant term is good enough. So we will see that understanding in our module 2. Yeah. All right. Yeah. So now we complete. Next, we start part D, the title, Optimality of Algorithms. Another important concept we need to study. Optimality of algorithms. D.1, minimum selection problem. Remember? So in our 3 basic types of algorithm problems, the third one, selection problem. But our D.1, we studied the simplest selection problem, finding the minimum. That's the simplest one. All right. Problem number 5, find the minimum of an array. Yeah, that's a simple question. Yeah. But we will learn the important concept, optimality concept. All right. Given an array, find the index such that A of I is the minimum of the array. Yeah, so simple. Yeah. Everyone can solve it easily, right? Yeah, here. Problem type, selection type. All right? Yeah. So the reference here, I give you, the sections. All right? Yeah. First, I want to give you the definition of selection problem. So when we talk about selection problem, what do you mean, the selection problem? Yeah. The definition is find the kth smallest element in a given array, but that k is given. Okay, the k number, little k number is given. Yeah. This minimum problem, that's a special case of the selection problem. When k equals 1, so find the first smallest element in a given array. All right. Finding the maximum. Yeah, another special case. Now, k equals n, finding the maximum. And so on. Okay? All right. Yeah. Now let's do some analysis. Because the algorithm part is so simple, so we can quickly go through the algorithm details. Yeah. Initialization, when you start, you initialize a variable min. Yeah. So we use this variable. At the end, we want this variable provides us the final minimum, the overall minimum, global minimum. All right? Yeah. Initially, we assign a of 0 to this variable. After that, the general step, we do comparisons. So each iteration, we compare this main variable with the current element, a of I. And we want to see which one is larger, which one is smaller. So there are two cases here. We consider two cases. Yeah. All right? Yeah. The first case, mean is strictly greater than our current element, a of I. Yeah. The current element is smaller. That means we can update this main variable, its value, with a smaller value. Yeah? If we change its value by the value of current element, then the value of this main variable becomes smaller. Yeah? So we want the smallest possible value for that main variable. Yeah. That's the first case. Yeah. So this is the assignment. We do the update. Yeah. Second case, yeah, the second case, less than or equal to, that means no update. Yeah. So we don't need to do any update. We just go to the next comparison. Yeah. All right. So another iteration, yeah, yeah. Compare main and a of I plus 1. Yeah. Then we do the similar process. Okay? We do the similar process. All right. Yeah. Until we reach the end of the array. After we reach the end of the array, because we go through all the elements in the array, then the value that is stored in this main variable should be this global minimum. No? Global minimum. Okay? All right. No. All right. So then, at the end, we return the value of this main variable. So that's the algorithm implementation details. Yeah, very easy. Yeah. But our main focus of this section, not at the algorithm part. Main focus here, that's the concept, optimality concept. That's the most important topic in this part D. All right. Yeah. First, let's look at number of comparisons we need when we implement this algorithm. Yeah. We want to count the number of comparisons. Yeah. All right. Yeah. We go through all the elements. There are n elements, right? So we go through all the n elements. All right? Yeah. But for the first element, we do not do comparison. So this is assignment operation. Main equals a of 0. That is assignment operation. So we do not count it as comparison operation. Okay? Yeah, assignment operation. Yeah, but because our goal, we only want to count the number of comparisons. So the first element, we do not count. Other than the first element, for each of the remaining elements, we count one comparison. Yeah, because we need to do one comparison. Yeah. So the total number of comparisons, n minus 1. Okay? Yeah. So the final answer to solve this minimum selection problem, n minus 1 comparisons. Yeah. Very easy to see it. All right. But the question, yeah, our main question is the following part, main question. Is this number the best we can get? Is it possible we can improve this algorithm slightly? That's our main question. Okay, main topic, main concern here. Yeah, all right. That's the optimality. Yeah, so yeah, I mean here I talk about how to see it. Yeah, because we here I want to use this chance to review the, counting by reference. Remember? Yeah, counting by reference. Yeah, yeah. All right, yeah. So that one, for each element, one-to-one correspondence, but the first one we do not count. Yeah. So you just see. So one element corresponds to one comparison. Yeah. But the first one do not count. Yeah. So that's why you have n minus 1. One-to-one correspondence. Yeah. All right. Yeah. Yeah. So here I still I list one-to-one correspondence. Yeah. All right. Review a little bit. Yeah. Next, now I want to go to the next step. Now, is it possible to further improve the algorithm? Is the previous algorithm the best we can get? No. So that's the optimality question. Now, to answer this question, there are two possible ways we can take. So two options here. The first one, improve the algorithm. No, because we always want to get the best we can get. No. So we should try very hard to improve the algorithm. That's the first option. But sometimes we may not be able to improve. No, you try very hard, but you couldn't. No. So then in that situation, we need to take the second option, convince people that the current algorithm is already optimal. No, there is no chance people can improve it. Optimal. That means nobody can improve. All right. So for our current problem, finding the minimum, our current problem, we have the efficiency number n minus 1 comparisons, that number. We want to see if that n minus 1 comparisons is optimal or not. If people can find a better solution, for example, n minus 2, is it possible that someone can find a solution with n minus 2 comparisons to solve the minimum problem? Yeah. All right, so that question, important here, the optimality. Yeah. Post-solution thinking, yeah, after that, we should try to improve solution as much as we can. Yeah, but we may fail, right? Yeah? So even if you try very hard, so you may fail. The solution may have been optimal already. Now, we feel we are not able to improve that n minus 1 solution. So we consider the second possibility. Yeah. Probably the current solution already optimal. Yeah. But if it is optimal, how to see it? How to see it is optimal? How do you convince people it is optimal? Yeah. So we need to do that part. Yeah. Convincing people it is already optimal. Yeah. All right. So the next discussion, the optimality discussion. Yeah. This is the hard part. So usually when we work on the optimality part, usually it is very hard. Yeah. Fortunately, because this problem is simple. Yeah. So for this simple problem, this optimality part is not that hard. Yeah. Not that hard. Yeah. But we need to pay a lot of effort to understand the optimality part. Yeah. All right. The harder part, how do we see the optimality? Yeah. The harder part is we need to address this point. What's that? Among all the possible algorithms, how to show that this one is optimal. Yeah? Because when you show some algorithm is optimal, you should cover all the possible algorithms that solve this particular computing problem, right? Yeah. You cannot miss anyone, right? You cannot miss any algorithm. You need to cover all the possible algorithms that solve this particular computing problem. But the question is, and there's all the possible algorithms, right? Yeah. How can you do it? All the possible. This part is hard. How can you cover all the possible algorithms, right? Yeah. Yeah. Including unknown. Yeah, because most of the algorithm possible, they're unknown. Yeah. People do not know the details of those algorithms. Okay? Unknown. Yeah. And they have not been developed. Yeah? They have not been developed. Unknown. Okay? That's the hard part. How do you cover unknown algorithms, right? In your discussion, how do you cover unknown algorithms? That's the hard part. All right. Yeah. How do you study those unknown algorithms? Okay? Unknown algorithms in general. Unknown. How can you study unknown algorithms? Yeah. Yeah. Is it possible to study unknown algorithms? Yeah. Another question, right? Unknown. Yeah. Yeah. All right. Yeah. Another question. Yeah. Some people may not feel it's possible, right? Yeah, because since they're unknown, how can you study? No way you can study unknown algorithms, right? Yeah. 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 By the logic, by the general logic, it looks like no way to study unknown algorithms. Yeah. But actually, if you think deeply, you can study. Yeah. There is a possibility people can study unknown algorithms. Why? Why people can study unknown algorithms? Yeah. Yeah. Because people can use a smart strategy to study unknown algorithms. Okay? A smart strategy. Unknown. To cover all the unknown algorithms. What's the smart strategy? Yeah. The strategy is discover some common property. Yeah. Although those algorithms are unknown, but we have a chance to discover some unknown properties of those unknown algorithms. Unknown property, common properties. Although the details of those algorithms are unknown, but they share some common properties, and we can find those common properties. Right? If we can find those common properties, we can use those properties to study all those unknown algorithms. That's the main point I want to convey here. Okay? All right. Let's see how to do it. So the next round, we want to do it. We want to see the analysis work, the arguments to convince people our algorithm is optimal. Common properties. Okay? All right. Yeah. We need some imagination based on the real world experience. Yeah, because here the main discussion, the main arguments, all based on our view, our understanding of the current problem. So we need to try our best to understand the current problem. How do we understand? So we apply our real world experience to help us understand the current situation better. So what kind of real world experience? The experience, so we're familiar with, playing sports games. Okay? Playing sports games. Yeah. Yeah. For example, the current World Cup. Yeah. 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 But the current World Cup, we want to use the analogy of the next round, elimination round. Yeah, because the current round, still not the best to make the connection. But the next round, elimination round, then that fits our current problem well. All right, so we can use that. Our comparison, we compare the values of two elements. That's like a game. Yeah. Two teams or two players. So they play each other. Yeah. So then we look at the possible outcomes, right? Possible outcome. The possible outcome, for each match between two players, the results, the outcome, okay? One is less than, less than, okay? So one number is less than the other number, it's just like, because here, our goal, we want to find the minimum, right? Minimum means the smaller the value, the better, right? Yeah. In that way, when we make our selection, we want to choose the smaller element. Yeah. So if one element is smaller than the other one, we pick the smaller one as the winner. Okay. Less than means a win. Okay. Not greater than means a win. Yeah. So we interpret it differently. Okay. We set our rules slightly different. Yeah. So less than means a win. Equal, a tie. Then greater than a loss. Yeah. So lose. Yeah. So three cases. Yeah. Yeah. But all right. Here in this one, because this equal case tie, it happens in the real world, but in our current problem, we know sometimes it happens, but there is a common way people can use to simplify. So when we solve a problem, sometimes we want to make our problem as simple as possible. How to make our problem simple as possible? Yeah. So because this equal case, when we do discussion, it's not convenient. Why it's not convenient? Because it does not belong to the win case, right? It does not belong to the lose case. Win case, lose, it does not belong. So we have a third case, so not convenient. Yeah. If we have two cases, win and lose, then it's simple, right? Yeah. So for that reason, to make our problem as simple as we ignore this case. Okay? But the question is, how can you ignore that case, right? Because in the real world, this case could happen. How can you ignore? Yeah. We can. Yeah. Why we can? All right. Here. Actually, this step is important. Ignoring this equal case. Yeah. Important. Yeah. All right. So we make assumption. We make our assumption here. So although the original question, we do not say that all the elements are distinct. Yeah. But here we add assumption. So this assumption, we add it. Okay? Although no such assumption, but we add it. We assume all the elements are distinct. Under that assumption, then the equal case is gone, right? Yeah. Under this distinct uniqueness, the elements are unique. Under this uniqueness assumption, the equal case is gone. Then it's simpler, because we only need to talk about win and lose 2 cases. Yeah. All right. But the question is, how can you do that? Right? How can you do that? Yeah. All right. Yeah. Yeah. So here, the idea we can do that. Actually, it's a common way people do it, make this assumption. All right. Yeah. Yeah. This idea is called, you can modify the given problem to make it simpler. Here we do modification of our given problem to make it simpler. Yeah. It is slightly from the original given problem, but it's okay. Because our first round, we work on the simplified version. That's our first round. Okay? The second round, we can go back to the original problem, right? Yeah. Why you cannot do it first round, second round, right? We do it multiple rounds. The first round, we want to work on the simplified version. This is our first round, okay? All right. Yeah, so no problem, you can do it. Yeah. All right. Then, this time, we just consider win and lose 2 cases. All right. But there is another important consideration here. Yeah. Because when we do comparison, we follow the math rules, right? Algebraic rules. Yeah. But in the real world sports games, people do not follow the algebraic rules, right? In the real world sports games. No, no such things. Yeah. But we need to include algebraic properties. So the one we need to use the algebraic property, transitivity property. We need to use it. What's the transitivity property? Okay. If we have inequality PA greater than PB, player A is greater than, yeah, so player A beats player B, right? Yeah, PA greater than PB. And PB greater than PC. Okay? Then by the transitivity, we automatically get a PA greater than PC. Yeah. That's the transitivity. Yeah. So in algebra, we always have that property. Yeah. But in our real world sports games, we don't have it. Okay? Yeah. You cannot apply that. Okay? Yeah. So team A beats team B, team B beats team A. It does not mean team A automatically beats team C, right? So those 2 teams, they still need to play to see which one is better. Yeah. All right. But here, in our comparisons, we can use this property. All right. All right. So then, based on this property, there is another important understanding step. This is important understanding step. That is indirect comparison. Yeah. We know direct comparison, right? Yeah. 2 numbers, we compare each other. That's the direct comparison. Indirect, what's the indirect comparison? The 2 numbers, we do not do direct comparison, okay? Yeah. For example, PA and PC here, do we do one comparison between PA and PC? We do not do it, okay? But we know PA beats PC by transitivity, right? So this kind of, we call it indirect comparison. Between PA, we do not do a direct comparison, but we have an indirect comparison. Okay? Yeah. So that's the special phenomenon we need to use in our understanding. Okay? Now we are ready to make our final convincing arguments. After all the preparations here, now we are ready to our final convincing arguments. All right. Now, argument number 1. Now, we want to make a sequence of arguments, okay? Yeah. In our understanding of the optimality problem here. The first argument, remember, our goal to make this list of consecutive statements, because we want to explore the common properties of all those unknown algorithms. Now, here, in these consecutive statements, we explore the common properties among all the possible algorithms, including unknown algorithms. All right, the first one, yeah. The value stored in the main variable at the end, that's the final winner, right? The minimum, final winner, okay? All right, so that's our starting point. Yeah. Our next statement, it needs to beat all the other elements. How do you convince people the current mean, this number is the smallest? So you need to do this statement. You need to do this. You need to convince people this number beats all the other elements through comparisons. Yeah. But the comparison, we use direct comparison and indirect comparison, both types of comparisons. Okay? Yeah. If you can show this mean beats another element indirectly, it's okay, right? Yeah. It's fine. Indirectly, yeah. By transitivity, okay? This mean beats some other element by transitivity, no problem. Yeah. It's legal. Yeah. That's our second statement. Legal. All right. The third statement, if an element loses once, it is eliminated. Yeah. If an element loses once, it cannot be the final minimum, right? Yeah. It is eliminated. Okay. So, you know that's all the common properties, right? Yeah. Even for unknown algorithms, yeah, they should satisfy all these statements. Yeah. Common properties. All right. The next statement. Each comparison can only eliminate one element. Yeah. After one comparison, you have one loser, right? That loser is gone, right? Can you eliminate the winner? You cannot, right? Yeah, it's ridiculous. Yeah. So after one comparison, the winner is gone. Yeah. So that's ridiculous. Yeah. So you do not allow that, right? Yeah. Yeah. So that's the common property, right? So even for unknown algorithm, this statement must be true. Okay? Yeah? All right. Yeah. Then, now, we're near the end of our final statement. All right? All right? Yeah. So, yeah. So here, I put it in the parentheses. There is one small special case we may want to include here. Okay? Yeah. So why I include this small special case? Yeah. Eliminate at most one. Yeah. So we know it cannot be two. Yeah. You cannot, after one comparison, you eliminate two. No, impossible. But is it possible after one comparison, you eliminate zero? That's possible, right? Yeah. Because after one comparison, you eliminate zero new losers. You eliminate zero new losers. Okay? So here, I want to address the, pay attention to the difference. Yeah. So how can you, because we know one comparison, we have one loser, right? Yeah. So here, it means eliminate zero new loser. New. Yeah. Why new? Because there is a possibility that loser already lost in the previous games, right? So then you do not add a new loser. Okay? So why I include this? Okay? Yeah. Because remember we need to cover all the possible algorithms, right? All the possible algorithms should include many bad algorithms, right? There are many bad algorithms we also need to include. For bad algorithms, they may do some redundant work, right? Yeah. Yeah. There are many algorithms, they do comparisons, but That's the redundant comparisons. You do not need to do those comparisons because you do not get new information. Yeah. You keep doing the, you know, the work, that's useless. Yeah. So we include those useless, redundant work. Okay? Yeah. That's why for those bad algorithms, you know, after one comparison, you get nothing new. Yeah. That could happen. Yeah, that could happen. All right. So that's why eliminated 0 new loser. Yeah. Yeah. But you have at most 1, right? Yeah. So that's correct. Yeah. So each comparison you eliminate at most 1 new loser. That statement is more complete. Now we are ready to make our final statement. Okay? Yeah. All right. We need to, yeah, because our goal, in order to get a winner, we need to eliminate n-1 elements, right? Directly or indirectly. Yeah. You need to find n-1 losers. Then the only one left, that's the winner. But to get n-1 losers, how many comparisons do you need to get? Yeah. Each comparison, you can get almost 1, but you need to, eventually, you need to eliminate n-1, so you need at least n-1 comparisons, right? Yeah. Because each comparison, you can at most get 1 loser, right? The total number of losers you need to get n-1, so you need to use at least n-1 comparisons. You may need more, okay? Because you do redundant work. You may need more than n-1 redundant work. Yeah. But nobody can use fewer than n-1, right? Yeah. Nobody can, because you cannot cover n-1 new losers. You cannot cover all the n-1 new losers, right? Yeah. So that's the convincing argument. Yeah. All those statements we put together because they cover the common properties among all those unknown, all those possible algorithms, including unknown algorithms. Yeah. So that's we prove that our current selection problem, our solution is optimal. Okay? Yeah. So nobody can improve. Yeah. Yeah. All right. Yeah. So that's the, most important topic for this part. Yeah. All right. Yeah. Then, yeah, so we have a few minutes. Yeah. But although we cannot complete this topic, but I can give you the question first. Yeah. So next time we do the solution part. D.2, we want to apply the solution. Yeah. So finding the minimum. Yeah. That solution. Although simple, but very important. So we want to apply that solution to solve a new problem. What's the new problem? Finding maximum and minimum simultaneously. Yeah, so here, the question is, not separately. Do not understand you find the maximum minimum separately. So you find the maximum minimum in one round processing. Okay? Yeah. Yeah, simultaneously. Yeah, so that's what people call. Simultaneously, okay? All right? Yeah, yeah. The fastest design, a fastest algorithm that can find both maximum, minimum together, yeah, that problem. All right. Question. Here, we are given an array with n distinct elements. Here, yeah. So in our discussion, in order to make our discussion as simple as possible, so in my question statement, I put this distinct condition there. Yeah. So you don't need to make assumption. Okay? Yeah. All right. Question, how to find both maximum, minimum simultaneously? Yeah. All right. So this question a little tricky. Yeah, so we need to, yeah. But the basic solution we need to use here, yeah, finding the minimum, yeah, finding the minimum, finding the maximum, essentially the same thing. Yeah. All right. Yeah. So here, when we do it, yeah, so the understanding part, very important. Yeah. We need to set up the environment. So in our understanding, we set up computation environment more friendly for our discussion. Yeah. So what kind of computation environment? All right. First, let us understand our data. All right. Array. N element array given distinct elements. Yeah. So we do not need to worry about equalities. Right. Yeah. Here, in this part, there is one important method we use in problem solving, elimination method. Yeah. Here, let me do some review. Review this elimination method. Yeah. Elimination. Well, in our convincing arguments, we did that, right? Elimination method. Yeah, we did it. Yeah. So here, let me review. When certain elements do not satisfy the criteria. Yeah. So given problem, there are some, criteria. Yeah. So you need to find, some elements with this particular criteria. But in your data processing work, if you can already identify certain elements that do not satisfy the criteria, then why you keep them there, right? Yeah, you do not need to include. So we can eliminate them from consideration. Yeah. You do not need to cover those irrelevant elements, right? Yeah, they're irrelevant. Why you include? Why you still keep them there, right? Yeah. So that's the basic point of elimination method. Yeah. It looks like trivial, right? Yeah. Yeah. So based on your current understanding, you feel that's natural. Yeah. For everybody you know, that's the natural way people should do it. Yeah. But in real world situation, many people do not realize they should do it in this way. Yeah. Yeah, many times, people always keep the irrelevant elements in the play. They always keep, because they do not realize they should remove them. So they still keep them. If you keep them, what's the consequence? The consequence, you do redundant comparisons. That's why, that's the reason. Yeah. Why people do redundant comparisons? Because they keep the irrelevant players in the game, right? Yeah, that's the reason for redundancy. Yeah. All right, so that's it.